This is the last of our look at Pythagorean theorem for this unit. We will continue throughout the course of the year to explore the Pythagorean theorem, but for right now this is the last of our 2 lessons on it. So, for example 1, given the right triangle with a hypotenuse of a length of 13 units and a leg of 5 units, as shown, determine the length of the other leg. So by using the Pythagorean theorem, plugging in what we know, 5 squared plus b squared is equal to 13 squared, we can go ahead and use our order of operations and our laws of algebra and conclude that b is equal to 12. So the length of the leg is 12 units in this case. This is one of the legs. Alright, so let b represent the missing leg of the right triangle. Then by the Pythagorean theorem, 5 squared is equal to b squared, or I'm sorry, 5 squared plus b squared is equal to 13 squared. If we let a represent the missing leg of the right triangle, then by the Pythagorean theorem, a squared plus 5 squared is equal to 13 squared. So which of these 2 equations is correct? 5 squared plus b squared or a squared plus 5 squared? Well, it doesn't matter which equation we use as long as we are showing the sum of the squares of the legs as equal to the square of the hypotenuse. So using the first of our 2 equations, 5 squared plus b squared equals 13 squared, what can we do to solve for b in the equation? Well, we need to subtract 5 squared from both sides of the equation. So we end up with b squared is equal to 13 squared minus 5 squared. When we're looking at the Pythagorean theorem in a form that allows us to find the length of one of the legs of the right triangle, that is, we want b squared is equal to c squared minus a squared. So therefore, b squared is equal to 13 squared minus 5 squared, which is 169 minus 25, which is 144. Well, we do know that there's a perfect number that we can multiply by itself to get 144, and that is 12. So the length of the leg of the right triangle is 12 units. So for example 2, the Pythagorean theorem as it applies to missing side lengths of triangles in a real-world problem. So suppose you have a ladder of length 13 feet. To make it sturdy enough to climb, you must place the ladder exactly 5 feet from the wall of the building. You need to post a banner on the building 10 feet above the ground. Is the ladder long enough for you to reach the location needed to post the banner? So here is the question, and it is probably good if you don't have a diagram to draw a diagram so that you know that the length of the ladder is 13 feet. It's 5 feet from the wall. So how tall is this from the ladder to the floor? So the ladder against the wall forms a right angle. We know we can use the Pythagorean theorem. We're going to let h represent the height of the ladder. So 5 squared plus h squared is equal to 13 squared. Or again, h squared is equal to 13 squared minus 5 squared. Using either equation, we see that this is just like example 1, and we know the missing side is 12 feet. So is the ladder long enough for you to reach the 10-foot banner location? Yes, the ladder allows us to reach 12 feet up the wall. Right, let's take a look at example 3. Pythagorean theorem as it applies to missing side lengths of a right triangle. So given a right triangle with a hypotenuse of 15 units and a leg length of 9, what is the length of the other leg? If we let the length of the missing leg be represented by a, what equation will allow us to determine its value? Well, we could say a squared plus 9 squared equals 15 squared, or we can say a squared is equal to 15 squared minus 9 squared. So let's finish the computation. A squared equals 225 minus 81. Well, that gives us a squared is equal to 144, and what number times itself equals 144? That would be 12. So the length of the missing leg of this triangle is 12 units. All right, go ahead and do exercises 1 and 2. When you have completed exercises 1 and 2, continue the video to check your answers. So here is exercise 1. If this is the triangle and we're missing a leg, then we can set it up as 15 squared plus b squared equals 25 squared. Show that we are subtracting 15 squared from both sides, in which case we get b squared is equal to 20, or b is equal to 20 units. And for problem 2, if we have a squared plus 9 squared equals 15 squared, that means that our leg length is, or the ladder must be placed exactly 12 feet from the wall. All right, let's take a look at example 4. The Pythagorean theorem as applies to distances on a coordinate plane. So we want to find the length of the segment AB on the coordinate plane as shown. So if we had a right triangle, we could use the Pythagorean theorem to determine the length of the segment. So let's draw a line parallel to the y-axis through point B, and we will also draw a line parallel to the x-axis through point A. So if you can see the red lines here that are parallel, you see that we form a right triangle. So how can we be sure that we have a right triangle? Well, the coordinate plane is set up so that the intersection of the x and y axis are perpendicular. The line parallel to the y-axis through B is just a translation of the y-axis. Similarly, the line parallel to x-axis through A is just a translation of the x-axis. Since translations preserve angle measurement, the intersection of the two red lines are also perpendicular, meaning that we have a 90-degree and a right triangle. So just going back to this, notice that these two lines are parallel. So here's the y-axis, and if we translate it, we also get a line parallel to the y-axis. Here is the x-axis, and this line has been translated, which means it is also parallel. So if we have a 90-degree angle here, if we translate it, we're still going to have a 90-degree angle here. All right, so now that we are sure we can use the Pythagorean theorem, we need to know the lengths of the legs. Well, count the units from point A to the right angle and point B to the right angle, and what are those lengths? So from B here and from A here. Well, the base of the triangle is 6 units and the base, or the height of the triangle, is 3 units. So what equation can we use to find the length of segment AB? Let's represent that by length C. So we would have 3 squared plus 6 squared equals C squared. So the length of C is 3 squared plus 6 squared equals C squared, which is 9 plus 36 equals C squared, and 45 is equal to C squared. We cannot get a precise answer, so we are just going to leave the length of C as C squared is 45. All right, example 3. The Pythagorean theorem applies to the length of the diagonal of a rectangle. So given the rectangle with side lengths of 8 and 2, what is the length of the diagonal? Well, if we let the length of the diagonal be represented by C, what equation can we use to find its length? Well, that would be 2 squared plus 8 squared equals C squared. So the length of C is 4 plus 64 is C squared, which means 68 is equal to C squared. Since we cannot get a precise answer, we're going to leave it as the length of C is C squared is equal to 68. All right, go ahead and do exercises 3 through 6. When you are done with those exercises, continue the video to check your answers. All right, so here is exercise 3. If we are looking for the line segment of A to B, we form a right triangle, and then here is the answer. Right, for problem 4, given a rectangle, what is the diagonal? So again, 5 squared plus 10 squared is 125. There is no perfect number that times itself is 125, so we're just going to leave it in terms of c squared. And for problem 5, you are just given a verbal description of a right triangle, and using the formula, we get 153. Again, there is no precise answer for that, so we're going to leave it in terms of a squared. And for number 6, you're given the hypotenuse and one of the legs. Again, b squared is equal to 105. Right, to summarize, we know how to use the Pythagorean theorem to find the length of a missing side of a right triangle, whether it be one of the legs or the hypotenuse. We know how to apply the Pythagorean theorem to a real-life problem, like how high a ladder will reach along a wall. And we know how to find the length of a diagonal of a rectangle. And we know how to determine the length of a segment that is on a coordinate plane. All right, we'll see you in class.